Good evening, guys. Good evening. Very good evening. Perfect. So now I think we can get started. We finished decision trees yesterday, right? Yes, guys. We finished decision trees yesterday. Okay. Let me save this. Today is day 9, right? That's for day 7, day 8. Yeah. Now let me upload the files for today. Mm-hmm. Yes, I'll just let you know what we need to download. I'm uploading an entire folder that has multiple case studies. We will be doing one case study here. So just download the classification. Just download this entire folder. Every data set and every file is already there. So you can just download everything that is there in day 9. Okay. Just download this classification folder. Yeah, you can just download the entire folder. You can just download the entire folder. That would help. Yes. The data, if you see, data has 500 columns. What is the first step? Do we need to check the missing extra first? We have to do PC and NDA? Yes, like because if there are any missing values or something, the PCA will not, it will not run smoothly. It will give error if there is any missing value in the data. So definitely before we do PCA, LDA, anything, we need to check for the missing values. The data should not have any missing values. If there is some missing value, the PCA will not work. Yeah. Okay, just download the classification folder, guys, and we can start the we can start some coding. We have ensemble learning left, but that is again similar to the that is something that is some sort of derivation from decision trees. So we'll talk about that while we do the code itself. Okay. Yeah, we haven't started anything. Just download the file. Just download the classification folder. We are going to start the coding and other things. Just download this classification folder. Okay. Yeah. You can just download it. You don't need to upload it somewhere. We can directly access it from the downloads. Download and unzip it. This folder, this classification folder. Just download the entire folder. Just download the entire folder. Yeah, you have downloaded it. You have downloaded it. I will let you know what we need to open from here. Let me know once it's downloaded for everyone. Done. Perfect. Now, I don't need this. Yeah, we need to open the classification algorithms, guys. We need to open classification algorithms file. Okay, just import the classification algorithms. Perfect. So now, again, this is a classification problem because we need to predict something that is in category. So we will observe the data and we will try to see what all algorithms we can implement and how, which algorithm is giving us the best accuracy. So first of all, we are just importing the libraries and then we are reading the data set. Sure. We are importing the library and we are reading the dataset. Now animals.head will give the top 5 records. We have 28 columns, right? In those 28 columns, that is somewhat related to the horse medical conditions. That is surgery, age of the horse, hospital number, rectal temperature, pulse, respiratory rate, and there are much more medical factors. At the end, we have, I think, outcome. Yeah, here it is. There is the column outcome. That is the target variable, and outcome has 3 categories: died, euthanized, and lived, right? So what's going to be the outcome for a given horse, whether the horse is going to die, he will live, or he will be euthanized? So basically there are 3 categories, 3 class classification, right? 3 class classification problem. right? And we have some data. Yes, right, euthanized or left. That is the data set. Clear, everyone? The data set is clear. Some medical factors, some medical conditions of a given horse and its outcome. Its outcome. And that is what we need to predict. We need to train and we need to predict the outcome for the new horses. Right? So how will we do? We will do with, we just need to predict the outcome. Right? We just need to predict the outcome. Whether died left or euthanized. Yes. That's what we need to predict. Clear? Perfect. Now let's see the outcome variable, died, left, euthanized, and let's store it in the target variable. If we check the only unique function, it will give us the 3 unique values. Okay. Now we stored the data into animals variable that is having all the input variables, right? All the x, all the input factors here. Clear? Yes, excluding the target variable. So we simply have the inputs and the target here. Okay. Perfect. Now let's observe the animals column, animals data set. So we have a lot of columns and we see there is a lot of missing values also in some of the columns, right? Yes. In some of the columns, there are lots of missing values, right? Now let's see percentage of missing values, missing percent. So yeah, this will tell us what percentage of data is missing in every column, right? Yes, we need to drop the column that has more than 30% data missing, right? How will we find? There is a isNull function, so we can simply use isNull to check the missing values. So we simply used isNull function, and here we have, right? So now whichever column has more than 30% data missing, yeah, we can also use mean. We will drop that column. So this will return the list of all the columns where we have more than 30% data missing. Okay. Yes. So now this cell number 11 will simply return the name of all the columns where more than 30% data is missing. Easy? Easy? Awesome. Now we will simply be dropping the rows, the columns where the number of missing values are greater than 30%. Done. Okay. Correct. Yes, anyone wants to answer why we why we didn't use mean or something? Yes, anyone wants to answer why we have not used mean here? Or like mean or any other approach why we have not, treated the missing values? We drop the columns which have more than 30% data missing. So these are the columns where more than 30% data is missing. That's why we are dropping them. Now after dropping the column which have more than 30% data missing, let's see what is left now. Now we still have some columns where the data is missing, but that's not more than 30%. So again, most of the columns are categories here. We can definitely go ahead and try to understand each and every column and find a best way to deal with the missing values. We can also, like right now, just to make it real quick, we are iterating and we are replacing all the missing values with mod. Okay. Just to be quick here, we are iterating for all the columns, and if there is something missing, we are replacing it with the mod. Make sense? Yes. Now, like we can definitely spend some more time. We can definitely spend some more time here to understand the columns and pick a more accurate strategies. But right now, just to be make it quick, we are using mod. Anyone? Yes, guys. Why we are using mod? What are the nature of the variables here? Categorical data. What we use in case of categorical data? Correct. Perfect. So now we are simply iterating and replacing everything with mod. Okay. No, that data type is not for the columns. We can't check the data type like this. This data type is for the series, and series is returning the percentage. That's why it's float 64, right? Okay. Now after executing this, if we check the missing values, there is nothing missing anymore in any of the data. Easy? Easy? Yes guys, there is nothing missing in any of the data anymore. Clear? Awesome. Which part? Yes, which part should I repeat? Yes guys, anyone wants to address what is mod? Right? And why, when we use mod, why we use mod? We use mod to fill missing values in the categorical data, right? We use mod to fill the missing values in categorical data. So right now, most of the columns are categories. That's why we replaced all the missing values with the mod of that column. Code number 16, isNull.sum will give us the sum of missing values. IsNull.sum will give us the sum of missing values, right? And if we divide it With the total number of observation, it will give the percentage of missing values. Dot shape 0 will return the total number of observations. Yes. Correct. Yes. Is any, is null, you can use any. Perfect. Now after this, let's see at the data once again. So that's how the data is. Let's see the float 64. Okay. Hospital number, that's int. So hospital number is integer. What exactly is going to be its nature, guys? Categorical, continuous, or what? What will be, what can be the nature of hospital number? It's going to be discrete. It's going to be discrete. If we check the number of unique values, 283 samples are unique out of 299 values. So hospital number cannot be a continuous because we cannot be sure that hospital number is having some range or something. And like when we talk about a continuous variable, its mean, standard deviation, and variance are something that are helpful for us, right? So the average of hospital number is, that is of no use. We cannot use the average of, average hospital number or something. Hospital number is basically to identify the hospitals. So that's going to be discrete, and we should drop this column. We should drop this column. Perfect. So now we are dropping the hospital number from here. Now selecting all the columns, in place equals to true, we specify if we want to save the change into the original object. We are dropping hospital number, in place equals to true, will save this drop in the animals column itself, right? We dropped the hospital number, in place equals to true, will simply drop it from the animals data itself. Otherwise, it will only return if we won't use in place equals to true. Yes, yeah, exactly. Animals equals to animals dot drop. Instead of that, we can use in place here. Clear? We dropped that column because it was discrete. We dropped that column because it is discrete. Okay? Yeah, like ID. Perfect. Now we are simply returning all the string type of columns and we need to encode them, right? We are checking all the columns that are having data type object, means they are textual, and we need to encode them. So we can simply encode them with the getDummies function. Yes. We need to write entire object. We can't use string because in data frames, object is what used for text data. Okay. Great. Now we simply returned the list of all the columns that are textual, stored it in a categorical variable. That's how it looks like, right? This is easy, I think. This function select d types will only access the columns that are of object type, and dot columns will give the column names only. Yeah, that is what we can also do. We can just check each and every specific column type, and we can go with that, certain approach. If it is ordered, we can use label encoder. Otherwise, we can go with the get dummies. Right now, like we can use get dummies here. Most of them, if you see, no, at the age is something that can be label encoded. Rest everything is nominal. Yes, only age is ordinal, rest everything is nominal here. Right? I think only age is ordinal, rest everything is nominal. So we know how do we encode and everything, we can do this thing. Yes, guys? Reduce normal, cool normal. This is also okay. Age, this, peripheral pulse, reduced, normal, increased. This is also ordinal. Extreme pain, this is also ordinal. This is also ordinal. So few of them are ordinal. 1, 2, 3, 4. 4 columns are ordinal. Right? 4 columns are ordinal. Okay? Basically, right now we are trying to do the categorical variable encoding. We used to do this when we have something in text, and the text columns are mostly categories in nature. Encoding means we want to convert them to numeric. We convert the text column to numeric with get dummies function if they are nominal, but we can go with the label encoder when they are ordinal, right? So right now, definitely this is a right way that we can actually go to each and every column specifically, and to uh, identify whether it's ordinal or nominal, and based on that pick a right strategy to encode the columns, right? Though we have already done this, we have already performed this method, so we can do it. Yes, guys? Right? The pre-processing thing, we can easily achieve this. Just a sec. Let me check. Get dummies increases dimensionality. We use get dummies whenever we have a nominal data, right? We do get dummies whenever we have a nominal data, and in get dummies there is a separate column for every variable, right? Every category. Now if we see how decision trees work, decision tree will check whether each and every category is significant or not. So we can do more better feature engineering when we have a separate column for every category. We can decide whether each and every category is significant or not. Make sense? Make sense? The benefit of doing get dummies over label encoder is that every category is going to have a separate column. And when it comes to the feature engineering, when it comes to observing the significance in the columns, we can analyze each and every categories differently, right? And we will see the decision trees in other algorithms, because yesterday we observed decision tree used to pick, used to decide the splits by itself. Now decision tree is the smartest algorithm that can ignore the irrelevant columns by itself based on the entropy. And when we train a decision tree, this algorithm also returns which column is important and which column is not important. We will get that information from the decision tree itself, right? Make sense? Yeah. Also, they are also very sensitive to overfitting, but in that case, we have some methods to deal with the overfitting in decision trees. Okay, go tell here. Everyone is clear what exactly we are doing in this case? We are trying to encode the data. Perfect. So we simply created the list of columns that are categorical here, and simple getDummies function will do the thing. This is how our data looks like now. Everything is encoded and we are having around 46 columns. Okay. Clear? Now again, their scaling can also be done. We can also do the standard scaling or whatever scaling is required. We can do, we can implement PCA, LDA also to extract the linear discriminants and principal component analysis and then build a model. That are also some possibilities we can do, right? And that can be an assignment to explore and experiment with the data and see how the accuracy comes. Okay, so I'll leave these things up to you guys. Try to explore with the data set, try to go with the different methods and the different, transformation techniques, and observe the accuracies, right? We can do this thing. We have already performed all the codes, everything, so we can execute, we can implement those things on this. We also know the steps, when what can be done, what needs to be done at what step. We also know that thing, right? Yes, guys, we have already discussed the steps to follow machine learning problem. So we all know that which needs to be done at what point. Actually, it was there in that other data set, but right now it's not there. Ideally, when we used to get something new, we need to check for the things, but these are the assisted practices, right? So we have already done all the possible cases and we made them optimized. So those mistakes and other things are not actually the case in this data set. Okay, make sense? Make sense? Right? These assisted practices are basically already optimized, so we are going a direct way. We are following the specific methods to solve the problem. But yes, all those things what we are doing here right now, we are exploring what all the possible methods we can follow, we can do, because this way there are a lot of things, not only checking for the spellings. There are a bunch of methods, bunch of steps that we can check, we should check in the data set, right? So this way, when we solve multiple different case studies, multiple different problems, we will explore the different methods, different steps, what we can do on the different types of use cases, and that's how we will get more possible exposure. Once we finish this, I'll share you a few more cases, few more data sets and solve case studies to explore some more practical approaches on the data sets, right? Make sense, guys? Everyone? Yeah, the way we shared for the linear regression, that has the different methods for the feature engineering, that has different methods for the scaling and other things, right? We shared few cases for the linear regression. So similarly, we will also share a few more cases for classification and others. Okay, perfect. All good till here, everyone? Awesome. So now the target variable is also there. So X is all sorted, but target is like this. We also need to encode the target variable, guys. We also need to encode the target variable. And what exactly is the right approach to encode the categorical variables, guys? What is the right approach to encode the categories? This is the target variable, guys. This is the target variable. MLE is not an encoding method. MLE, maximum likelihood estimator, is not basically to encode. That is how logistic regression going. Okay, what about this, guys? What should be the right approach here? This is the target variable. What exactly needs to be the dimension of target data, guys? Correct. Correct. So we need to do label encoders, right? So we are doing label encoding in our target variable, that is this. These are the this is how our target variable looks now. Correct? This is how the target variable looks now. Clear? The labels will be assigned as per the alphabetical order. So E, D, L. Based on the alphabets, it will give 0, 1, and 2. Map can also be used. We can also use map here. Okay. Awesome, guys. Fit transform is basically to transform the data into a label encoder. That's how we do the label encoding. Yeah. Perfect. All good till here, everyone. So we simply did the data pre-processing thing. LE is the assigned variable. LE is the object of label encoder. LE is the object of label encoder, and we are invoking the fit transform function from the object of label encoder. And we are giving the data that needs to be transformed. Y was this earlier, but now after the transform, this is how Y looks like, right? Okay, just to do a quick recap, what we have done so far, we simply did the read CSV, we deal with the missing values, right? And we checked the after the missing values, and we checked the categories, we encoded the categorical variables, right? That's all what we have done here. That's all what we have done here, right? Clear, everyone? Okay. Now, what all possible things we can do? The feature engineering, PCA, LDA. Now, this is something up to you guys. You have to explore, you have to experiment on this data set. Try doing scaling, try implementing the feature engineering methods, principal components, linear discriminants, and then build algorithms and other things. Right now, our aim here is to understand the algorithms, because pre-processing is something we have already covered. We have already done the pre-processing steps, and we have also implemented the pre-processing thing. So right now we can explore the pre-processing. Yeah, we can do EDA, we can explore the pre-processing and other things. Now we need, like, our aim in this case study is to understand the classification algorithms, right? How exactly we can build the classification algorithms, what are the different parameters we can tune in classification algorithms, and let's see which one gives the best accuracy. And also the evaluation, how we evaluate the classification algorithms, right? Exactly, exactly. So the pre-processing thing is something we can do, right? We can cover, we can implement the pre-processing part in this data set. Yes, guys? That makes sense to everyone? So now let's move further and let's do the train test split. We are simply executing the train test split function, giving x and y, and the test size equals to 30%, right? Right? Simple splitting. We have already done all these splitting things, so this also makes sense, everyone. Okay, now let's see the train and test data set. 209 observations will be used for training and 90 observations will be used for testing. 299 observations were there, right? So 209 are being used for training and 90 observation will be used for the testing. Clear, everyone? Let me check. Okay, here it is, the KNN, and the random forest is something we have not covered. So I'll be doing a little bit of rearrangement in this file. Decision tree and random forest needs to be done at the last because that's how we have discussed. Okay, let me KNN, then support vector machines, then naive Bayes, and here should be decision tree, random forest, and then ensemble. Okay, perfect. Perfect. All sorted. So first of all, let's implement the first algorithm, that is KNN. So we have talked about its theory part, how KNN works, right? We know how exactly KNN works, everyone? Yes, we had already discussed this thing. Okay, now let's implement the KNN. First of all, we have to import the class for no nearest neighbor, right? From sklearn.neighbors import KNN. We just need to import the class no nearest neighbor, kneighbor classifier. And once we have imported the class, we will simply be creating an object for the kneighbor classifier class by specifying how many neighbors we want to check, right? Okay, now this number 3 can be anything. We can give 3, 5, 7, 9, 11, and there are lots of possibilities. We can give any number. This basically means how many how many neighbors we want to check, we want to observe while predicting for the new observations, right? We used to pick this number such that we don't get any biased result. Okay, we need to keep it in such a way that we don't get anything biased. I'll show you. Like I'll just like once we will see the fit on 3, we will see the fit on some other functions, other numbers also, and we'll see which one is giving the best accuracy. So now simply creating the kneighbors classifier. Now fit function will simply train. So that's done. Training has been done here. Dot score will give us the training score and test data is giving us the test score. X test, Y test. So 63% is the testing accuracy and 80% is the training accuracy. The model is overfitted, right? The model is overfitted. Perfect. Now let's try to observe the accuracies on different numbers of n neighbors. So I'm simply creating a list neighbors where we will be having the different integers, right? So if we see the neighbors are having 2, 3, 4, 7, 6, like the entire from 2 to 9 numbers. We will be training and we will be checking the accuracy at every neighbor. Make sense? We have trained the algorithm. Dot fit function will train. Dot score function will give us the accuracy. So when we give train input and train output, it gives the train accuracy. When we give test input and test output, it gives the test accuracy. Okay. Now that's 79%, 80% or 63%. These values are something that is how many observations are being classified correctly. So we had only 99 observations out of 99 observations out of uh, on testing data. So out of 99 observation, only 63 observations are being classified correctly. Out of 100, 63 are being classified correctly. So that's going to be, actually, I think it's going to be quite similar for the 99 observations as well. So this is what we are getting as a accuracy. Correct? Correct, guys? Clear, guys? If Kenan score of train is less than the test score, that's the case of underfit. Basically, when the train score is less, we don't check the test score because model is not even giving the accuracy in training. So we don't go for the test score. If the train score is less, definitely it's a underfit model. And if it's an underfit, means either the algorithm is not best for the specific data set, or we need to work more on the data pre-processing part. Okay. Sure. The cell number 39 here, we are checking Kenan dot score and we are giving train X and train Y, right? We are giving train X and train Y. So it is going to give us the score on train accuracy, right? It will give the train score. We are giving test X and test Y. So this will give us the test score. Yes, guys, it is giving the test score. So this is the testing accuracy and this is the training accuracy. Clear? Okay, how do we get to know overfitting, guys? Anyone? How do we get to know the overfitting? If the model is overfitted or not? Yes, training accuracy much greater than test accuracy. Higher magnitude, that was the case in linear regression. But apart from that, how do we check the overfitting? The training accuracy is much way higher than the testing accuracy. And right now we can see the training accuracy is 80% and the testing accuracy is 63%, right? So it's an overfitted model. Now let's see what we can do. We are creating a neighbors list where we have different numbers, right? So we are going to use these numbers as n neighbors and see what's going to be the accuracy of algorithm, right? What's going to be the accuracy for the algorithms? Now we are simply iterating for I in neighbors list. Kn equals to k neighbors classifier and neighbors equals to I, right? So that's simple object creation. That is a simple object creation. If we get train 64 and test 68, can we say no? In that case, it's not overfit. In that case, see, when we get train accuracy less, we don't need to trust the test accuracy, because if the model is not giving accuracy on the same data what it has been trained on, we can't trust on the accuracy on the unseen data, right? It could be a by chance case that we are getting a good accuracy, but we should not trust that. Yes? There is no such threshold for the accuracy. In some cases, we have 60% as brilliant. In some cases, even 90% is something we reject. So it completely depends upon the data set and the business case. It completely depends upon the data set and the business. Yeah, there is no standard accuracy score like 100%, 90, 80. There is no such threshold to be accepted. It completely depends on different data sets and what exactly is our end requirement. Yeah, correct. Clear, guys? Everyone? Awesome. So now for I in neighbors, we are creating a KNN object, kneighbors classifier, where we specify n neighbors equals to I. So I is the number that is coming from the neighbors list. So it will be creating different objects with the different values of n neighbors, training on trained data, and again we are saving the test accuracies. So now if we plot the test accuracies, we have not imported Seaborn. Okay. So the training is done on the different values of neighbors. We trained and we stored the test accuracy, knn.score, test x and test y. So we are appending knn.score, test score on that specific knn in the accuracies list, right? We are only appending the test score. Yes, guys, we are appending the test score. That could be different because of the different data set in train test split. It could be different because of different data set in train and test. We can have different data set. We can have different graphs because we have different data sets into training and testing. Yes, if you start from the beginning, re-execute the train test split, the graph will be different. In line number 43, we are iterating the number of neighbors we are training for different values of n neighbors. So knn equals to k neighbors classifier and neighbors equals to I. I will be the value that we are accessing from the neighbors list. We are iterating from the neighbors list. So this way we will be creating multiple knn objects on multiple different values of n neighbors, right? First 2, then 3, 4, 5 and so on. Then we will be training on the train data, knn.fit, train x train and y train. See the second line inside the loop, we are just training the knn object what we have created here with the n neighbors value I, and then we are simply appending the test score in accuracies object. Accuracy is an empty list, right? It's an empty list. We are appending the test score for every train in accuracies object. Clear? Clear, everyone? Yeah, definitely. If we implement PCA, LDA and other things, the accuracies are going to be different. And I believe we are going to get some better accuracies in knn specifically if we do LDA. But it's for the exploration, guys. I'll leave these things up to you. Please explore and try to see what's the change, what's the difference. Okay, there will be a lot of exploration in this case study. I'll give you a lot of other things to explore and test on. So let's understand how we build an algorithm. Now we need to do different types of pre-processing techniques. We need to play with the data sets and we need to build these algorithms again and again. Okay. Perfect. knn is clear? Okay, now you can pick the number whichsoever is greatest. So for me, it's saying 2 is the greatest, so I can keep the neighbors 2. And if I train and if I check the train accuracy and test accuracy, 66% is the test accuracy. And yes, it looks good. So see, the accuracy, the test accuracy is not improving much. It's still overfitted. The test accuracy is not improving much. The test accuracy is still from 63 to 66%. What we can conclude in such cases, the training accuracy is no matter like it's 84% or whatever it is, we are going to accept the test accuracy only. Means if we are finalizing this model, we will be saying the model is giving somewhere 65-66% accuracy only, right? What we do in such cases, what we do in such cases, if we need to conclude, if we need to finalize this model, we will be finalizing this model over 65-66% accuracy only. We will be saying that our model is able to give around 66% accuracy. Make sense? But definitely we should explore the other algorithms also. So let's proceed and let's see how the other algorithms are working. Okay? It's still overfitted. It is still overfitted. We can't say it's not overfitted because the training accuracy is 84 and testing accuracy is 66. So again, there is still overfitting, 18% of difference. So model is still overfitted. And if it's still getting overfitted, we can, like we can't help it much in KNN. We can try other algorithms. Or if we want to conclude on this specific case only, what we used to do if we have such kind of scenarios, what we used to do, we can conclude the model by accepting 65 or 66% accuracy. Okay, that is a possibility because the train test split is different. How we can overcome this issue also, like for some iteration it could be 66, for some iteration it could be 75. How we can actually overcome that issue? By the cross validation we discussed in the last class, grid search. So grid search used to do this thing multiple number of times with different types of splits and gives the average accuracy, right? So having different splits, different random samples and different accuracies, we can get over this issue by using cross validation approach. Yes guys, there could be a possibility that in some specific iteration, we are getting the highest accuracy, and in some specific iteration we are getting the lowest accuracy. So we can simply use the cross validation approach, and based on the different types of splits we can decide. Yes, the cross validation, the grid search will do the hyperparameter tuning along with the cross validation. Means it will do the train test split multiple number of times and observed 3-4 test accuracies and gives the average test accuracy, right? Yes. So this problem can be resolved using cross validation approach. Okay, we will talk about the solution guys, we will see. I'll show you in a while. Let's discuss the algorithm first, then we'll discuss about that in more detail. Okay, let's complete the algorithm and then we'll move to that part. That is there right here in this file. If we scroll down, it is there implemented, so we'll talk about that in more detail. Perfect. Clear everyone? The KNN is clear? Perfect. Now let's see the support vector machines, and that's what mathematics we talked about, the support vector machines. This is how support vector machines work, right? Maximum margin, maximizing the margin. Remember we had discussed the support vector machines. Now how we train a support vector machines? So in order to train a support vector machines, we simply import support vector classifier CLF equals to SVC. Like again, a very standard approach of training any machine learning model. We create an object first, we invoke the fit function, and we check the scores, right? Now see, we are not getting any good scores at all in this case. 61, 57, 4% of difference is there. We can't say it's overfitted, but it's not a good score. Yes, guys? It's not a good score. So there is still some parameters what we can tune in hyperparameter tuning, specifically for support vector machines, right? Specifically for support vector machines. So let's see to them. Like earlier, we were getting 66% accuracy, but right now the accuracy got reduced. That's how we can say it's not a good accuracy, right? Earlier, the test accuracy was 66, but right now it's 57. So definitely it's not good, right? Perfect. Now there are few parameters. C and gamma in SVM. So we can actually play with this C and gamma values in SVM to make the model more accurate. And we will just see how these values can do a huge, can impact on the accuracy on a very huge difference. Okay. So first of all, we need to understand what are these C and gamma. Before we utilize the C and gamma, let's understand what are these C and gamma. So we can see this data hyperplane distribution, right? This is the simple classification support vector machines built on different values of C and gamma, right? See, right now we have different hyperplanes built with the different values of C and gamma. So we need to observe how exactly C and gamma are impacting the hyperplanes. First, let's observe the change in C. Let's observe the change in C. This is the increase in C. This is the C. Okay? Smaller to largest. Now see, if the value of C is increasing here, the hyperplane is trained in such a way it is trying to classify every outlier into a specific class, right? When the value of C was small, this was not being classified correctly, but the values of C is being increased and see the hyperplane is getting changed to make this observation classified into a right space, right? Yes, this is capital C. This is basically a regularization parameter. When we try to increase the value of C, see the value of C is increasing here. The hyperplane is being tuned in such a way that each and every observation is trying to be classified into a right space, making it more accurate. And this also makes this sense that if we increase the value of C too high, the model is going to get overfitted. If we increase the value too high, the model will get overfitted, right? Yes, makes sense. So how this capital C is going to behave in support vector machines? Is it clear, everyone? Sure. So if we see the value of C is increasing from this to this point, and as the value of C is increasing, the hyperplane is trying to make each and every observation into a right side of the hyperplane, right? As the value of C is increasing, it is trying to tune the hyperplane in such a way that it will try to make each and every observation at the right side of the hyperplane. And see right here, it like almost it's there because it cannot classify it properly. It cannot classify this one properly, but it made it. Yes? Yes? Makes sense? Got it? What C is doing? Now, C is not exactly the data. C is basically, we talked about an equation yesterday. C is one more factor that is being added to that equation in order to tune the hyperparameter correctly. Yesterday we talked, no, that's not mx plus c. This is capital C. It's not that mx plus c. This is a separate. Remember, if we go back to the linear regression, there was a penalty term, right? In Ridge and Lasso. Similar to that penalties concept, that equation of hyperplane in SVM also have such elements that can be used to tune the hyperparameter, tune the hyperplane. Similar to the penalty concept in linear regression that we have in Ridge and Lasso, the sum of square of magnitudes and the sum of square of magnitudes, right? We used to have some penalty term in the cost function of linear regression. Similar to that concept, we also have some elements in SVM also in order to tune these parameters, tune these hyperplanes. So one of those element is C and another one is gamma. That is something we can actually play with to make the algorithm more accurate. Make sense? Yes, guys? Perfect. Now, this is completely not ax plus by plus c equals to 0, that c. It's not that c. It is a complete different element out of those variables. Okay? So, understood how this component is going to behave, how this component is going to impact in our hyperplane? Is it clear, guys? How this component is going to impact in our hyperplane? This is clear, everyone? C component? Perfect. Now, observe the gamma. Observe the gamma. So, this is where we are increasing the value of gamma, right? This is where we increase the value of gamma. And see, as we increase the value of gamma, the distance is being more optimized. The distance to the observation is being more optimized, right? Here, if you see the as we increase the value of gamma, the distance from the hyperplane is being more optimized. And see, now this has a specific enclosed area for every observation. Now this is not going to be like this. We are observing it in two-dimensional space. Definitely that's going to be in multi-dimension and there will not be any enclosed hyperplane. But this is just trying to like we need to understand here that as we increase the value of gamma, the distance is being more optimized here, right? Yes. So in order to have a good accuracy, we need to tune these values of C and gamma in such a way. We need to tune these values of such an C and gamma in such a way that we get the ideal accuracies in train and test both. Yes, guys, the values of C and gamma needs to be tuned in such a way that we get some ideal accuracy in the train test and the test set both, right? So now these values are something what we have in our hand, what we can play with, what we can change and tune to get some better accuracy on a given data set, right? Make sense? So when we train support vector machines and if support vector machines are not giving any accuracy, we are not helpless. We can actually play with the values of C and gamma to make the model more accurate. Okay, make sense? Make sense? Okay, now let's understand what should be the good values of C and gamma we should check for. Now let's understand what exactly is the good values of C and gamma we should check for. In case of C, we try to explore more digits like greater than 1 digits like 0 0.1, 1, 10, 100 like this. Ideally, we should go like this 0 0.1, 10, 100. We need to explore more digits greater than digit places greater than 0, greater than 1, and here we explore more decimal digits, more decimal places. So we started from 0.001. Actually, it should be 0 0.1, 0 0.01, 0. 0.0001 and then 0.0001. Okay, so this way we should start. This is how a good start on C and gamma is, right? This is how a good start on C and gamma should be. A good start, right? Now suppose if the value of C is selecting this, now we should go more decimal places and explore more the values of gamma. Suppose after this start, it says that this is giving the best accuracy. So definitely we should try more smaller numbers to see if we are improving, we are still improving. Make sense? Yes, guys. How we can start the good values of C and gamma? Is it clear, everyone? A good start for C and gamma. Is it clear? Perfect. So we are again doing grid search CV. Oh, we have not imported it. Yes. Grid search CV, it is there in which, just a sec. Here it is, model selection. Grid search CV is there in model selection. Okay, we have created a grid CV, trained. Best parameter, see the value of gamma is actually decreasing. It's the least value what it has picked. Yes, the value of gamma what it has picked is the smallest value. So now we should explore more, right? 0.0001, 0.00001, right? Make sense? Yeah, we put the values of C to explore more digit places, and in the place of gamma we have explored more decimal places. Okay, clear, guys? Understood? Yes, if it picked the value of C as 100, we should explore more bigger numbers for C, right? It completely depends on what exactly it is picking. It picked 1, so we have given the possible cases 0.1, 1, 10 and 100. If it would have like picked 100 or 0.1, then we should have gone for even lesser numbers, or we should have gone for even bigger numbers. If the best parameter for C was 0.1 or 100, right? So that's how we used to change. For gamma, it picked the smallest number what we gave in the parameter grid, but it was not having much flexibility to go even smaller. That's why it picked the smaller. So we should give more smaller numbers then. Make sense? Yes? Yes, guys? Make sense? How? Yeah, please. If we decrease gamma so much, this can make our model biased, right? No, actually, if this it will only get us the test accuracy. It will decrease and it will give us the test accuracy. So whatever we are getting is on the unseen data only. So we can be very sure that this is not going to be biased, right? We can be very sure here. For me, it's even giving the smaller value. We can be sure why we are not going to get the biased results, because the grid search CV is going to get us the test accuracy. If there would be any biased algorithm or a biased training, we won't be getting a good test accuracy, right? Because test is a completely unseen data. Make sense? Perfect. Can you please keep your pace? So yeah, I'm so sorry. Are we going more faster, guys? I'm so sorry. Definitely we can go, whatever is comfortable. Please let me know. Are we good, or if there is any challenges, guys? Anyone? Cell number 59 is basically we are creating a grid search CV object where we specified our estimator, means classifier, what we have created here, right? We have created a support vector classifier, CLF object. So we specified CLF object here. Then we gave the parameter grid, what parameters we want to explore, the cross validation, and the verbose, what amount, how do we want grid search CV to display the process of execution. Okay. Okay, we'll reduce. We'll go slow now. We'll go slow now. Perfect. Clear, guys? Grid cell CV is clear, everyone. Support vector machines is clear, everyone. Let me know if anyone have any question anywhere, please. If there is any question from anyone anywhere, please let me know. Line number 61 can have different outputs. Possible, it could be a possibility it can have different outputs. Okay. C and gamma are actually the parameters in support vector machines through which we can actually tune our hyperplane to get more accurate results. So if we increase the value of C, the hyperplane is being tuned in such a way that it will try to classify more accurate observations. Right? If we increase the value of C, it will try to tune the hyperplane in such a way it will try to classify more accurate observations if the value of C is being increased. And if the value of gamma is being increased, the distance will be more optimized. Okay? Yes. Any other questions, please? Cell number 56. It should be a dictionary with the key as a parameter value, right? The format of cell number 56, it's a dictionary where key is the name of the parameter, that is capital C, and the value is the possible values on C what we need to give, right? So we need that format needs to be exactly same, not for the support vector machines, for other algorithms also. So the key is the name of the parameter what we want to tune, and apart, like, the value for that key is the possible values of that specific parameter what we want to check. Okay. Yes, it will give whatever we specify. It can't give anything in between. It can only give us the best values where we have, it will only give the values where we have the best accuracies. It can only check for the values what we give. Means if we are giving 1 and 10, it can't give anything between 1 and 10 then. It can either give 1 or 10, whichsoever is the best. Okay. It is 5 because there must be 5 in the values of here. If it is 5, you must have given 5 here some in that code, in that file. There must be 5 in this list. We can't specify the range. We need to give the specific values. We can't specify the range. We have to give what specific values we need to check. We can't give the range in parameter grid. All good, everyone, about the parameter grid and grid search CV, C and gamma. CV equals to 3 and verbose. Yes, guys, anyone wants to answer what is CV equals to 3 and verbose? We have done this. We have already implemented the grid search CV in Rage and Lasso. Got it? CV is the number of cross validations we want to do, and verbose is what amount of what amount of information we want to display about the process of execution. How fast, what is happening inside the grid search CV, what are the total number of iterations and everything. How we want to display that, that is the verbose, and CV is the cross validation. Clear? Yeah. Awesome. Perfect. Now clear everyone, the grid search and also the support vector machines. Perfect. So now let's again explore more on gamma and let's see what's the best value. So it is still giving e raised to the power minus 5. It is actually still giving this value. So let's again go more smaller. Yes, the best value of gamma is even smaller now. So we can try going it more smaller. It's keep on decreasing. Let's see what is the accuracy, guys. 65%, best score is 65%, and when we didn't give this, %. Okay, so now see, we should stop at this point only because the best testing accuracy is 71%. So we can stop at this point. Yes, guys. So now let's observe the difference also from 57% to 71%. A big change, a big increase in the accuracy. A big increase in the accuracy here. Yeah, that's this value. That is this value. Scientific notation of numbers. Right? Okay, clear everyone? Yes, right now, right here we can say the SVM is more accurate than the support vector machines. Okay. Now let's train a model for these specific values of C and gamma. Yeah, 79% train accuracy and 70% test accuracy. Yes, on that specific value of C and gamma, the train accuracy is 79 and the test accuracy is 70%. Clear everyone? Best score line 78. Based on all these possible parameter values, grid search dot best score, it will give what is the best score we are getting on the C10 and gamma this. It will simply tell us the best parameter. These are the best parameters where we get the best score, and what was that best score? That is this. Easy? What is the good score? Good score means the overall accuracy what this model is giving is 70%, and we can say it's good because we are getting better than the previous algorithm. What are the most recommended values of C and gamma? Guys, there are no, actually, whenever we work on any algorithm, you know, or any specific case study, everything depends on the data. There will not be any such standard goods things or some standard, rules we need to follow. That everything depends on the different data distributions, because there are lots of variations possible in the data set, right? There are lots of variations possible in the different data sets. So everything, be it the accuracy, what should be the threshold on the accuracy, or what should be the good values for the parameters, completely depends on the data sets. So we need to implement this grid search CV and these kind of algorithms to get the best out of a given algorithm. Make sense? Yeah, exactly. We need to give different values, and we need to finalize which one is giving the best. See, again, there should not be a huge difference. Somewhere 5%, 5-7% is okay. If we are having some 5 to 7% of difference, that is still okay. But if we have a very huge difference, like 20% or 30, 15, 20%, then we say it's actually a overfitted model. And if there, like, after doing everything, we are still getting a difference in the train and test accuracy, we finalize that model on the test accuracy only. Right now, there is a difference of 9%. So at the end, if we are concluding on SVM, we would say that our algorithm is giving 70% accuracy on this data set. We won't say that it's giving 79%. We will say it's giving 70%. Make sense? What error you are getting? In real time example, dataset keeps changing, then how to decide the C and gamma? Like, we need to decide the C and gamma at one time when we train the data, and training data doesn't change that frequently. Yes, the value of C and gamma is something that we only decide when we need to train the data. And in also real time scenario, we won't train it very frequently. It's not fitted. Okay, you need to fit it first. You cannot execute any code, the score or something like that. You need to create an instance variable, you need to fit, and then you need to execute the score functions. Okay, you just need to train the algorithm first, then we can use the score and other functions. Without doing the fit, it won't be able to give the score. Yes, clear. What would be the case when we put the algorithms on fly? Basically, when the data set or when these models are in production, they don't get trained again and again. They only give the predictions. And for getting the predictions, we don't need to give the values of C and gamma. The values of C and gamma are something we only give when we need to train the algorithms, right? Okay, sure. So we can conclude SVM. So we can proceed with the further algorithms after the break. Yes, guys? The SVM is clear? Everyone? Mean training, their hyperparameter tuning, and everything about SVM, the code part, how do we create an object, how we train the support vector machines, what are the C and gamma, how we decide the values of C and gamma. Few major things. How do we train support vector machines? Simply create an object, use fit function, right? There are two parameters, C and gamma, in support vector machines that can be finalized using grid search CV. Once grid search CV gives the best values of parameters, again create a new instance variables for support vector classifier by specifying these parameter values, right? Right? Creating a new object of support vector classifier by specifying the hyperparameters, executing .fit function to train the algorithm and observing the scores. You need to import grid search CV from sklearn. I will update this file again, guys, because I have made few changes. So you just need to execute this code. I'll update the, I'll upload the updated file. There are few changes what we have made here. So I'll upload this updated file, guys. Okay, I'm sorry. What are the reasons why the CLF score may increase closer to 1? How a CLF dot score gets closer to 0 when changing the kernel inputs? You mean to say, basically, while different executions, it may a little bit fluctuate because of the different data distribution during train test split, right? It can change. It can change based on the different data splits. It can also change based on the values of C and gamma, because C and gamma are some elements that helps us to tune the hyperplane in order to get improved accuracy also, right? The values of C and gamma are also some elements in support vector machines that can help us to tune the this hyperplane in order to get some improved accuracy. So sometimes we get some improvisation, sometimes it made it more worst, right? So that's why we need to intelligently play with the values of C and gamma using grid search CV. Make sense? Yes, guys, make sense? Okay, that is because of, okay, you have done the hyperparameter tuning. The model got overfitted. The model actually got overfitted, right? That's why we are not getting, you are getting the good accuracy in training and not that good accuracy in testing. Okay, so we actually need to pick these numbers quite intelligently so that we can get a good accuracy. We can get a generalized model at the end. Clear, guys? Yeah, exactly. There is a lot to manage, guys. There is a lot to do in uh, while dealing with the problems. Okay, now we can go on a break, guys. We can go for a break. Perfect. Let's get back after 15 minutes, guys. Hey everyone. So we are all back. Awesome. Awesome. Perfect. So let's continue and let's see the other algorithms. Sorry. Naive Bayes. So let's see how exactly we can implement the naive Bayes. Basically, naive Bayes, we have two different forms of naive Bayes, Gaussian and Bernoulli. But right now, none of them will be, accurate for our case. Why so? Because Gaussian is the one when we have continuous inputs, right? Gaussian naive Bayes is when we use continuous input, right? And Bernoulli, binary classification. Okay. So in none of the cases, our data set fits. Yes, guys? The Gaussian form of naive Bayes is used for continuous inputs and Bernoulli is used for binary classification. But in none of the cases, our data set will fit, right? Because we have three class classification and input variables are also categories for us. Yes, guys? In our data set, we have three classes. In our data set, we have three classes and also we don't have the continuous inputs. So that means Bernoulli is actually not a good option here to train on, but still we can give it a try, whether like by any luck or so we get some accuracy. But yeah, ideally by the concept of Bernoulli or Gaussian, naive is not a good fit here. So actually, then we are losing information in that case, right? If we are losing one class, then we are losing information in that case, right? So that again will not be a right approach. So we can, like, if we actually want to try, we cannot use Bernoulli because it's only for binary classification, but we can give it a try to Gaussian. We don't have continuous, but it will treat those categories as a continuous variable itself, right? It will treat those categories as a continuous variable itself, but we are not getting any good accuracy at all in this case, right? And that also makes sense because naive Bayes is like by the Gaussian or Bernoulli itself, we were not having a right, approach for implementing the naive Bayes here. Yes, guys, it doesn't seem a good fit. The naive Bayes doesn't seem a good fit for the data set. So though we have tried it, but we are not getting any decent accuracy. 58% is actually not a good because 70% is something we were getting in support vector machines itself. So we can ignore the results. We can just ignore the naive Bayes and we can move to the next algorithm. Yes, guys? Make sense, everyone? Yeah, because we have two forms of naive Bayes, Gaussian naive Bayes and Bernoulli naive Bayes. Gaussian naive Bayes is used when we have continuous input variables. Bernoulli naive Bayes we use when we have binary classification problem, right? So none of the naive Bayes algorithm is actually it's actually fitting in our case, right? For our data set, we have categories and also three class classification. So that's why the naive Bayes algorithm is actually not, yeah, for the but like in the implementation part, we have two types of naive Bayes, Bernoulli and Gaussian. right here. For our data set, it's not actually being, it's not fitting for any of the case, neither in Gaussian nor in Bernoulli. Still, we can give it a try that we implemented the Gaussian, but it was not getting any accuracy. The best we get is, the best accuracy what we have got in this case is 58%, and that's not good because we have already achieved 71% accuracy in support vector machines, right? Make sense? So we can move to the next algorithm because Naive Bayes is not getting any good accuracy. Yes, guys, we can proceed to the next algorithm because Naive Bayes is actually not getting any good accuracy. Yes. How do we actually implement the code? It's exactly same. We need to import, create an object, use the fit function and the score functions, right? Instead of Gaussian, just import the Bernoulli, and that's how we can use the programming part, the programming pattern. It's same for all the algorithms, right? Linear regression, the SVM, the KNN, or what all algorithms we have covered so far. The programming thing was same for all. Yes, guys. The program is same for everyone, right? Perfect. Easy. Great. Now, the next algorithm what we can train is decision tree, and we know how decision tree classifier works and everything, right? Perfect. So importing decision tree classifier, creating an object of decision tree classifier, fitting 100% train score, 63% test score. Highly overfitted model. Perfect. Now, the classifier.predict function can make the predictions, right, on the training data. So xtrain is the train input, xtrain is the input data, the predictors. The predict function will make the predictions and store it somewhere. So this line of code is clear, everyone? Right now, from the trained object, we are trying to make predictions on the input data. Yes? Perfect. Then we are predicting on the test input. So X test is the test input. We are making predictions on the X test and we are storing it in pred y test, predicted y for the test data, right? Easy. So what are these two results? What we have in pred y train and what we have in pred y test. the predicted values. The predicted values. These are the predicted values from the input variables, right? Yes. Now, there is a accuracy score function that can compare the actual and predicted values. So see, in this accuracy score function, we are giving the predicted values and actual values, right? Pred y is the predicted y train and this is the actual y train. No, that is there for all the other variables, all the other algorithms also. This predict function is there for all the algorithms. The programming pattern is same for all. We have dot score for all, we have dot predict for all. Similarly, we have dot fit for all, right? So this predict is also available for other classifiers as well. We can also use this predict function for KNN, SVM and other algorithms also. Okay? Right? Perfect. Now see this line of code. We are trying to give actual and predicted values in accuracy score function, right? We are giving the actual and predicted value in this accuracy score function. Yes? Perfect. The accuracy score function will simply compare the actual and predicted value and it will also give the score. So that is the another method to calculate score, right? Easy? So that's what we were actually getting in this also. It means all the observations are being classified correctly from the training data, right? All the observations are being classified correctly from the training data. So we can use any way. This is also telling us the accuracy and this is also telling us the accuracy. And actually they are also giving the same accuracies. We can use anything. Why I have also placed this code here, because let's suppose you are working on some GitHub project or you are exploring some Kaggle kernel. So you might see this accuracy score function also, right? So this is also a way we can calculate the accuracy. Yeah. Exactly. But there is a difference. In the score, we are giving input and output. But in accuracy score, we give actual and predicted output. Right? In score function, we'll give input and output. But in accuracy score, we give actual and predicted output. Actual output and predicted output. Right? Perfect. Okay, now we need to work on this overfitting case and let's see how we can handle the overfitting. Clear, everyone? Okay. So also yesterday we discussed about the overfitting. We discussed about the overfitting and we saw that there are two parameters, max depth and minimum sample leaf node, right? Max depth and minimum sample leaf node to take care about the overfitting, right? Either we can limit the depth of the tree to some specific number. We should not split more than that depth, or we can also have some minimum samples in leaf node, right? Yes? Right? So max depth and minimum sample leaves, we need to tune these values for the decision tree. And again, we can use data CV for the same. So best it can give is 65% accuracy, not a very good increase from 63 to 65. Yes, not a very where are these numbers come from? 1, 2, 3, 4, 5. These are basically some ideal numbers what we can pick. Yeah, sure. See, we know how the decision trees work, right? We know how the decision trees work. Yes? So, the minimum sample in leaf, these numbers should be in the terminal node. We should have like a split should be classifying at least 5 observations, right? It should not classify less than 5 observations or at least 3 observations. So as per our intelligence, as per our understanding, we can give any number over here. Yes? Got the idea behind how we decide the values, these numbers? These numbers should be a split should be at least classifying these many observation. It should not be like we have created a split only for one observation to classify only one observation or so, right? Make sense? Make sense? Yeah, we can increase the depth. We can increase the depth, but if you see, increasing will not help us to deal with the overfitting. See, increasing the depth will not help us to deal with the overfitting. We need to restrict the depth. So even if at the 5 we are not getting a good test accuracy, see at 5 we are not getting good test accuracy. If it will go beyond 5, definitely the test accuracy is going to decrease, right? Increase will not help us to get better results. Make sense? Perfect. Easy decision trees. Parameter grid means what all parameters we want to test on. That is the parameter grid. Okay. That is the parameter grid. Clear? With these predictions, what are we concluding? Right now, we are not making the predictions. Right now, we are not actually making the predictions. We are training and we are checking the model's accuracy. Right? How do we make the prediction? How do we make the predictions? By using what is the classifier? Classifier dot predict. Okay. We have the X data like this. Let's suppose I want to use the 0th observation only. Okay. Yes. So let's make the prediction for this. The shape. So we need to give the array dot values dot reshape -1 1 comma -1. Yeah. So it is predicting as array 0. So we simply made the prediction for the first observation. That is saying 0. So we have 3 classes: died, lived, euthanized. So D will come first. So 0 stands for D. 0, 1, 2. So this is died, this is euthanized, and this is lived. So when we made a prediction for the first observation, it said 0, means the first observation what we had here will die. This horse will die. Got it? How we make predictions? Because we are giving the array like this. See, we are giving this as a training data, two-dimensional, right? Number of rows and the number of columns. That's what we are giving in training. That's what we are giving in training. So we need to give the testing data also in same shape. We need to give the data to make the predictions also in same shape. So we made it like one row and multiple columns, one row and unknown columns, right? Got it? How we make the prediction for the specific record and why we need to reshape, just to make sure that we are making it in the exactly same shape how we trained the data, right? And if we simply give the x, it will predict for all. It will predict for all. uh like there is no direct way to visualize the tree. We can definitely visualize, but there is a certain specific library called GraphViz through which we can visualize. Now again, there is no straight way with the GraphViz also. It will give you an annotated text file. It will give us an annotated text file, and we need to copy that text file. We need to go to their website, paste that text file, and they will visualize the tree, right? They will visualize the tree. So there is not actually a straight way to do this thing. Reverse transform will help here. Inverse transform will give us the exact values. Okay, understood the decision trees, guys? Everyone clear? Awesome. Clear, everyone? I will upload this file. I will upload this file. Okay, now after this, what we need to understand is their evaluation. Okay, now the decision tree will also tell us the feature importances. Let me plot them. Hmm. So feature importances, classified.feature importances, it will also tell which feature was the most important and which feature is not that much important, right? This is the same way for all the algorithms. Yes, making predictions is same for all the algorithms, right? We cannot, it's up to us, because ultimately the decision trees will only pick the columns that are necessary, that are important. Decision trees and tree based algorithm will do everything by themselves, right? So we can, it's up, like if we change, or if we select or drop in decision trees, that's not going to make any change. But yes, for other algorithms we can try this. For other algorithms we can try this. And we also know how this feature importances will be calculated with the help of entropy, right? With the help of entropy, right? Perfect. So it is clear, guys, decision trees. Clear decision trees, everyone? Awesome. Now, let's see its evaluation methods. Now we need to, understand how we are going to evaluate these algorithms. Exactly. For every algorithms, we can do all these things and we can finalize which one is giving for every data set. Why it's not copying? Wait a sec. Control Command C, Command V. It's wrong. Okay, perfect. Confusion matrix. So that is something we have created on classifier right now. So let's see classifier, classification report, and also the confusion matrix. Okay, so now what is this confusion matrix, guys? First of all, let's understand the confusion matrix in binary class. Then we will see the confusion matrix in multi-class classification problems. We will also talk about the significance of these evaluation methods in classification algorithms and when to use when they are actually helpful. So first of all, confusion matrix. So the matrix itself is very confusing. That's why its name is confusion matrix. Actual, predicted. Let's suppose 0 and 1, predicted 0 and 1. Okay. Okay, cool. So this was actually 0 and predicted also 0. So this will be true negative. This is going to be true positive. This is going to be false positive. And this is going to be false negative. Right? So this was predicted negative and actually also it is negative. So this will say true negative. Right? Yes? Similarly, we have true positives. Similarly, we have true positives that actually that the actual label was also one and predicted also one. So they got true positive, right? Right? And similarly, we have false negative and false positives. So if we try to understand the confusion matrix in this case, 0, 1, 2, 0, 1, 2. Okay. Actual was 0, predicted was also 0. We have 66 such observations, right? Actual was 1, predicted was also 1. We have 36 such observations. Actual was 2, predicted was also 2. We have 164 such observations, right? Right? So now what exactly is this matrix is clear, everyone? Yes. This is a confusion metric. They named it confusion metric itself because it's confusing. Clear, guys? Yes. How many? Basically, actuals and predictions over the populations. Okay. Now, after this, we have precision. Oops. We have precision. Now, what is precision? Precision is true positive over true positive plus false positive. We have recall. Recall equals to true positive over true positive plus false negative. Okay, and we have a F score, F1, that is 2 into precision into recall divided by precision plus recall. Right? Now let's try to understand what is the precision and what is the recall. Okay? Let's try to understand what is precision and what is recall. See, true positive plus false positive. True positive plus false positive. This is total predicted positives, right? Yes? True positive plus false positive is total predicted positives. Let me use a color. Right? True positive plus false positive are actually total predicted positives. So this is telling us how many of them were accurate out of total predicted positives. Yes? This precision is actually telling us how many of them were actually correct out of total predicted positives. Right? Correct. What is precision? Similarly, precision can also be calculated for the negative class. That's going to be precision for class 0 will be true negative divided by true negative plus false negatives, right? That's going to be total predicted negatives. So this will be the precision for class 0. The way we calculated the precision for class 1, we can calculate the precision for class 0. How many of them were actually correct out of the total number of predictions? Out of total 0 predicted values, how many of them were correct? That's the precision. Clear? What is precision? Excuse me. Clear? Here it is telling us the true positives means correct predictions out of total positive predictions. Here it is telling the correct predictions out of total negative predictions. So we can simply calculate the precision for any class, for 0, for 1, and precision will simply give us the accuracy over the predicted values. If there were 100 predicted as well, how many of them were actual one as well? Got it? Precision is clear, guys. What is precision? Okay. Now, similarly, if we see the recall, recall is the confidence over actual population. The denominator of recall is true positive plus false negative. Right? True positive plus false negative. That is total actual positives right? Total actual positives. So it is telling us out of total actual positive populations, how many of them were also predicted as positives. So recall is giving us confidence score over the actual population, and precision is giving us confidence score over the predicted population. Got it? Yes, that is the sensitivity. Okay, and the F score is the average of precision and recall. F score is the average of precision and recall. Clear? The precision is the confidence over the predicted values, and recall is the confidence over the actual values. Okay, the precision is the confidence over predicted values, and the recall is the confidence over actual values. Clear everyone, the precision and recall? Perfect. Now let's understand where these precisions and recalls are going to be helpful. So we can calculate the precisions and recall for every class. So the recall for another class will be true negative divided by true negative plus false positive, right? This. That will be the recall for class 0. This is recall for class 1. So we can calculate the precision and recall for all the classes, right? Okay. Now let's understand their importances. If we observe the data set, if we observe the accuracy, okay, right now we are actually observing on the entire X and Y, but let's use only test X and test Y, okay? Instead of using the entire X and Y, let's only use test X and test Y, then we will be able to capture where exactly is the problem. Yes. Okay. So let's understand where exactly is the problem. See, we understood the precision recall. The precision and recall for class 2 is good. That's because there are more number of observations for class 2. Support is the number of observations. Number of observations, right? So for class 2, the precision and recall is still good, 74, 72%, because the number of observations here are more. Now, this can be for everyone. This evaluation can be done for every algorithm, every classification algorithm. This is just for, like, right now what we are evaluating is the decision tree only, right? Right now we are evaluating the decision tree, but this can be done for every algorithm. So see here, the precision and recall for the class 2 is good because the number of observations are heavy. 54 observations out of total 99 test observations. More than 50% data belongs to class 2, right? And see, the precision and the recall for these two classes are very less, very less. And that's because the number of data in those classes are also less. So if we observe the precision, recall and F score, we are actually targeting the class problem, right? Now we can say that data set, the problem is not because of the algorithms are not capable. The problem is because the data is not evenly distributed within the classes. Yes? Definitely there is more data for this class 2. So the predictions will be more biased towards the class 2. predictions are going to be more biased towards class 2, and there are very less observations for one, that is only 13 observations out of 99. So that's why the precision, recall and accuracy is very less for the class 1, right? Now makes sense why exactly the precision recall are very helpful, where exactly they are helpful. Yes guys. Isn't there more chances of having less predictions if the data is more? Sorry. In precision, wait. In precision, it is the confidence over predicted values. So what does 0.52 means? If there are 100 observations belong to class 0, only 52 out of them, if it is predicting 100 observation as 0, only 52 out of them were correct. Right? This precision 0.52 means if it predicted 100 observations 0, if the model is predicting as 100 observations will belong to class 0, only 52 out of them were actually 0. More data means more margin for error. I'm sorry, I still didn't get it. See, actually, in out of 99 observations, we have 54 observations belongs to class 2. So most of these splits are actually giving right predictions for class 2 only, right? And the splits do not have much information for 0 and 1 because the data is very less. The number in support is more than the precision. Support is actually the number of observations we have. Support is actually the number of observations we have. We have only 23 observations, we have only 13 observations and 54 observations for every class. Okay, got it? So if the observations are more, the accuracy, the results, the predictions will be more concentrated towards that specific class. Now, what is the solution? What is the solution? Make this data balanced. Make this data balanced. Create the subsamples. Don't use the entire data. Reduce the number of samples from 2. Make the number of observation little balanced. Okay, it was 90. Sorry, my bad. It was 90. Make the data little balanced. Okay. Make the data little balanced and try to execute all the algorithms again. Yes, it should not be exactly same 30 30 30 or 33 33 33. Somewhat that looks good, right? 35 35 30 30 30 40, that still looks good. So some balanced proportion should be there. Yeah, yeah. So now what's our task now? Go back to the data pre-processing step, right? Back to the pre-processing and just downsample the class. Means let's suppose we have 290 observations and we the like this minority class has only 50 observations, right? So use only 50 random samples from all the classes and then train the algorithm and see whether there is any increase in the accuracy or not. Okay, right? Make sense? Yes guys. Make sense? This problem is called imbalanced classes problem. This problem is very very common, and we get this problem wheresoever we have the imbalanced classes, wheresoever we have the imbalanced data set. Okay, clear guys, clear everyone? Yes, evaluation and these basic classification algorithms. Is it clear, everyone? Please let me know if there is any questions, anyone, or in the classification algorithms case study. Yes, right now we are only checking for the test data. I'll update this file. Okay. Now, no one asked about the macro and weighted average. What is the macro and weighted average, guys? What are these numbers? Yes. So why 56 and 64? Two different means. Okay, what is 56? If I ask what exactly 56 is here, what is 56? So what was 63 we were getting earlier? We were getting something like 63 or so. What was that? Okay, fine. If 56 is the accuracy, what is 57 then? And what is 63 here? Yes, guys? If 56 is accuracy, what is 57? What is 56? 63? Exactly. Average of precision and average of recall. Yes. Yes. See, this first line, let's understand the first line first. This is the average of precision. This is the average of recall. This is the average of F score. Right? Average of precision, average of recall, and average of F score. Clear? Now, this is weighted average. Weighted average means we have more observation for 74. This number will be given more importance. We have less observation for 43. This number will be given less importance, and this number will be given the importance as per its you know population. How we calculate the weighted average? So let me tell you how this 0.64 is being calculated. 0.52 into 23. I need more space. 0.52 into 23 plus 0.43 into 13 plus 0.74 into 54 divided by 23 plus 13 plus 54. That's how 0.64 is being calculated. This is called weighted average. Right? This is called weighted average. Understood? Perfect. So we know how to evaluate this confusion matrix as well, the classification report here as well, right? Sure. The F score here is harmonic mean of precision and recall. Yes. Or we can simply understand that F1 or F score. It's F1 score or F score, anything. F1 score. We call it F1 score only. There's nothing else. This has only one name, F1 score. The F score is telling us the overall idea about precision and recall. Perfect, guys. Evaluation is clear, everyone? Awesome. Now let me tell you one more trick what we can do. We can actually save a classifier to our, you know, to our primary memory. So we know whenever we restart this kernel, the training and everything will be lost, right? Whenever we restart this kernel or whenever we restart the Python, the training and everything will be lost. Need to run again. So there could also be a case where we have a huge amount of data and training used to take amount of time like hours or so to get trained. There could be a case, there could be a possibility where we have a huge amount of data and training takes a lot of time. We cannot train it again and again, right? So what we do in that case, we store the trained object. Classifier is the trained object. Yes. Right now the classifier is trained object. So we imported the pickle library. We have created a file with the name saved final classifier.pickle as write binary mode of opening, and we are dumping this classifier object. So when I'll execute it, we can see there is a final classifier, saved final classifier seconds ago. This just got saved, right? Yes. Now we can give this to anyone. We can share this file to some other server, to some other person, and that person can import and execute the predictions, right? Now we can share this pickle file. This is the trained decision tree model. We can share this, and anyone, like now let's say this is the saved one. This is how we are going to read this back. Open it in read binary mode, same file name, and we are simply doing pickle.load whatever is available in the f object, and we are storing it in a saved model. So when we do saved model dot accuracy, we will get the accuracy, right? Exactly on the same model. Why we are getting more accuracy here? Because we are checking it on x and y, the entire data, not on the test data. If I give the test data, it will be the same. Mm-hmm. Oh, score. So x test need to give 63%. Correct? This trick is also clear? Easy? Interesting? Awesome. Now, the next algorithms are ensemble learning algorithms, in which we have a lot of things. So we can discuss the ensemble learning and other things tomorrow. Yes. Yes. Okay. So we understood the programming pattern, we understood the coding, we understood the approach to solve a classification algorithm, everything. Yes. Yes, guys. The approach to solve classification algorithm, the basically concepts part, the programming pattern, everything. Clear, everyone? Awesome. Yes. So tomorrow will be the last class for the session, last session for the week, right? And then we will be having a weekend. So for the weekend, I'll give you 2, 3 case studies to solve. We still have ensemble learning to complete, so we'll complete ensemble learning, and then I'll give you 2, 3 case studies to solve. Perfect. So as of now, we just need to revise whatever we have done today. We just need to revise whatever we have done today. Next week, time series forecasting, unsupervised learning, that is 1 day unsupervised, 1 day time series, 1 day recommendation engine, and 1 day natural language processing. And then still we will be getting one ideal day that we can discuss about other things. Okay, so after we finish this, tomorrow we'll complete. Tomorrow we complete this, whatever it is, ensemble learning. Yeah, so tomorrow we will complete ensemble learning. Then we will be having 5 remaining classes: 1 day for unsupervised, 1 day for time series forecasting, 1 day for recommendation engines, and 1 day for natural language processing. And one ideal day we will get. Right? We can talk about projects, we can talk about anything. If you want to say, like, if you want to discuss about the deployment, the APIs, if you want to talk about neural networks, reinforcement learning. So we will be getting one ideal day. Whatever we want to discuss, we can talk about that. Yes, we need to complete at least one project within 15 days of completion of this day, this entire. Sure. Interview questions, whatever is required. I'll create a list of the important things. We can discuss that in the last day. XG Boost will be in ensemble learning. XG Boost will be there in ensemble learning. Okay. Yes. Yeah. The submission deadline can be exceeded if required. So started. Yes. Yeah, there is assessment test also. Simulation test. Okay, now we have time for Q&A if there is anything anyone wants to ask. So, a quick recap, what all we have done. We have covered everything about the classification approaches and like specific algorithms, what we have done. We have done KNN, we have done support vector machines and decision trees, and also we talked about the naive Bayes, right? We also talked about the naive Bayes. Great. Let me know if anyone have any questions, anything from today's class. First project, we will have a separate session to discuss about the projects. Don't worry about it. So once we finish the algorithms, we'll talk about how to solve each and every problem. We will discuss about every like all the three projects, what are the questions and how to solve them. Speech data, yes. Like is it some audio data or numerically some numerical factors extracted from the audio data? Audio data. Okay, so in that case, we need to extract some numerical factors from the audio data, or we can use neural networks to feed in the data. Like even if we have the audio files, MP3 or something, we used to extract some jitter, shimmer kind of factors from those files, frequency, wavelength, pitches, and we work on that. Let me upload today's file, otherwise I'll forget. Yeah, we are good to drop off, guys. And Paige, what is the upcoming challenges in the industry? If I talk about right now, what people are working on, what big companies are working on, are the transcription projects. Means if there is a conversation going on, or if there is a conference call going on, to transcribe all the voices, all the conversation. That's what the companies are working on right now. Even Google launched a beta version of their transcription API, in which if we have one-on-one conversation, or I think they have upgraded it to the multiple people conversation also, they can easily create the the conversation script. Yeah. Perfect. No questions? No one? All good, everyone? How did I learn these ML? How did I learn? I learned like not from BTech. I learned them in an organization. I joined there as an intern, and there actually I started implementing these things, and that's how I learned. Yeah. Perfect. That's everything. Practice, practice, practice. That's the only tip. More you can explore, more you can read, more you can work, more you can solve the projects, more better you can explore. Yes. I won't say the course or some, like the what we are doing is more than enough. After that, all you need to do is to work on the projects. Practice, Kaggle, GitHubs, papers with code, explore the data sets, try to solve the business cases, and that's the only way. No, actually, the courses, the certification degrees or something, they are helpful, but we can also achieve the things without them. Working already, it depends. It depends how many lives you can say. It completely depends how much you can lie. Yes, there is a lot of remote opportunities. Is it okay to lie when you do not have practical experience on the data science? Actually, the question should be, is it okay to tell the truth? Because most of the people lie only. Hmm. Can I work from home after ML and AI? Definitely, you can work from home. You can work from like we can easily get the remote work. If okay, let's talk about it seriously. If actually you are working on you are actually working on a full time role with some organization, it is actually hard. It's quite difficult to get any internship or part time role because most of the companies, even if it is a startup or any company, will not pick the candidates who are already working somewhere. Right. It's quite difficult. If you say that you are working part time, they will ask you to dedicate a given timeline. If you are looking for a part time role somewhere, they'll ask you to give a dedicated timeline. And if you are already working on a full time basis, you won't be able to give that specific 4 hours, 3 hours, or something. For past 5 years, yeah, same. Like not from 5 years, but it's been good time. I'm also working from home itself. I work from home, work from mountains, work from hospital, work from friends home. I've tried everything. Work from college, except work from office. Reinforced learning begins, then data science job will not. No, 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 it's not be like this. No, it won't be like this. YouTuber. Oh, I also used to get such WhatsApps. Perfect. Okay, I think we are all good, guys. Thank you, everyone. Thank you all. Thank you for being cooperative. Thank you for reacting on my lame jokes. I'll come up with better jokes from the next time. Thank you guys. Thank you everyone. Bye bye. Take care.
Thank you for the wonderful and thank you all for your participation. I request everyone to kindly fill the feedback survey form. The link is been already shared in the chat box. Please do fill the form.